Module 7, and we will have 2 chapters in this module, Chapter 20 on magnetism and also Chapter 22 on electromagnetic theory. So we're all familiar with magnets, and this ties into our study of electric fields also, because magnets can be altered by an electric current, and that's what this is showing right here. So we'll talk a little bit about magnets, magnetic fields, what happens to currents that produce fields, how we define magnetic fields, and that we use this term B for magnetic fields, what happens when you've got electric charges moving, what happens to the field if you're on a long wire, and then what happens between, say, 2 parallel wires. I'll just briefly introduce solenoids and electromagnets and talk about mass spectrometry, which is used quite often in chemistry as an analytical tool for the identification of compounds. So magnets have 2 poles. You've all probably seen this in elementary school, a north and a south pole, and like poles repel and unlike poles attract. So these diagrams are just showing you the difference between the attractive and the repulsive forces. If you cut a magnet in half, you don't get a north pole and a south pole, you just get 2 smaller magnets. So you can theoretically just keep cutting a magnet apart and you'll continue to get smaller and smaller magnets here with both a north and a south pole. So the way that we visualize this, and if we were in a lab, you would see this experimentally. If you took a magnet and you put iron filings here, which are attracted to magnets, you would see that what you get would be these electric field lines. And what's also interesting is if you took a compass, which always points to magnetic north, that it always points from north to south, and the field lines also always go from north to south. And the direction of north is always going to be tangential to these electric field lines. So as we move a compass around, we can see that they move the north facing compass is tangential to the field lines. So the Earth's magnetic field is similar to that of a bar magnet. And so the Earth's north pole is really the south magnetic pole, and the north ends of the magnets are attracted to it. So it's kind of the opposite of what we think, because remember, opposites attract. So we find that the north magnets are attracting to the south pole. Okay, when you've got a magnetic field, it's constant in magnitude and direction. So these are vectors also, because remember, vectors have magnitudes and directions. And if you look at a north-facing magnet, or a north pole and a south pole, and we have the attractive forces, they're always going to be from north to south, and they'll be essentially uniform across this distance or this gap. When you get to the end, you'll see it kind of floats a little bit due to the fact that you've got, pulling of the vectors one way or another. So this is similar to electric fields, where we go from positive to negative. So what we also seen is that if you take a current and you apply it to a wire, like here with a copper wire, that the current is always, the current produces a magnetic field. And the direction of the field is determined by what's known as the right-hand rule. And this is an important rule because it tells you, so if you take, and down here is showing this right-hand rule, if you take your right hand and point your thumb in the direction of the current, that's the current direction, I direction, and you curl your fingers of your right hand around, in this case, this wire, this gives you the direction of B. And we'll talk a little bit more about magnetic fields, this term B. It tells you the direction of the magnetic field. So a current produces a magnetic field. You can use the right-hand rule. There are 2 right-hand rules. We'll call this one right-hand rule number 1 to determine the direction of the magnetic field. So this shows it a little bit closer. It doesn't matter. Now here we have a loop, all right? And if the current is going downward, then using the right-hand rule, it's clear that the magnetic field direction is basically circular and up this way. So again, the right hand rule, you extend the right hand so the fingers point along the direction of the magnetic field. Or if you don't know that direction, you point your hand in the direction of whatever the particular charge is, or whatever term it is that you know. And in this case, the thumb will point along the velocity of the charge or the current, where this current is moving. And then the magnetic force is going to be perpendicular to that magnetic field. So if a charge is moving in a negative direction, the direction of the force is going to be opposite to that predicted by the right-hand rule. So you're going to assume that, again, if the moving charge is negative, then the force is going to be in the opposite direction. So in this case, it would be directly downward. So a magnet can also exert a force on a current carrying wire, and this direction of force is given by what's known as this right-hand rule number 2. So in this case, you'll see that the current, in this case, the current direction, and now I'm looking at this setup B, the current is moving towards the left-hand side of this slide. So those fingers are pointing in that direction. As you curl the fingers around, that's showing that, according to the right-hand rule, the magnetic field is pointing that way, and the force is directly upward. So again, this is the right-hand rule. Your fingers point in the direction of the current. As your fingers curl around, that gives you the direction of the field. So now, quantitatively, the force on that wire, the magnetic force, or the force, I'm sorry, depends on the magnetic field. And without going into the derivation of this, which is quite lengthy, we can come up with an equation that relates the force to the current in amps. So current here is in amps. To the length of the wire, this is the length of the wire, to the magnetic field, B is magnetic field, and the units for magnetic field are Teslas, and I'll show you this on the next slide. And theta is the angle, and the force is in newtons, so your angular measure is in degrees. So recall that if it's the sine of 90 degrees, that value is going to be 1, and the sine of 0 is going to equal 0. So those are typically the two cases that we'll see. All right, so the unit for magnetic field is known as the Tesla, and it's based off the units for force, current, and length. So 1 Tesla is equal to 1 Newton over an ampere times a meter. So just make sure when you're doing these problems that you have your units of newtons, amps, and meters, so that your unit for magnetic field is going to be the Teslas. Another unit that we use more lesson frequently is the Gauss, and that equals 10 to the minus 4 Teslas. All right, so here's an example. So say that you've got a speaker, and it's got a wire here that's coiled around, and that wire has a diameter of 0.0225 meters, and there are 50 turns of this wire. So if we want to find the length of this wire, what you're going to have to do is determine that based on the fact that this is the diameter of the wire. If we take the diameter times pi, that's the circumference of the wire. And then if we multiply that times 55, that's giving me the length of the wire that's coiled around this speaker. So that's the length. This problem is giving you the amps, the current. It's also saying that it's placed in a 0.10 Tesla magnetic field. And if you look at the angle here and make that determination, you'll see that the magnetic field is perpendicular to the force, so that angle theta is 90. And as I said, the sine of 90 is equal to 1. So that's causing me to put this 1 here for the sine of theta. And if you do that calculation, you'll get that the force is 0.086 newtons. And the second part of this asks you to find the acceleration of the coil in the cone. There is some acceleration as this moves back and forth. And to do that, you could just use Newton's second law, going back to physics 1, to find that force. So that's an example of that sort of problem. We can also have a force on an electric charge that's moving in a magnetic field. And in this case, again, I'm not going to go over the derivation of these equations because they can get quite lengthy. But the force on a freely moving charge versus one that's in a wire, because what we just saw was one that was in a wire. If it's just a point charge and it's freely moving, then that force is going to be equal to the charge itself, Q, times the velocity of the charge, times the magnetic field, times that angle. And again, the direction's given by the right-hand rule. So if the charge moves parallel to the field, all right here we're seeing that these two are perpendicular, then the sine of theta is equal to 90, or theta is equal to 90, and the sine of theta equals 1. Conversely, if F is equal to 0, is if the charge moves in the same direction as the field, because then that sine of theta is going to equal 0. So if a charged particle is moving perpendicular, its path is going to be on a circle. This should kind of look like uniform circular motion that we saw in physics 1. And you'll see that in each case, this velocity is tangential to the circle, and the force is pointing inward, just like we saw with centripetal force. B, and it's kind of tough to show, but if you use the right-hand rule, then B would be into the page in this case. And this right here is just showing the path of the electron. All right, so when you're solving these problems, remember that the force is perpendicular to the magnetic field. We use the right-hand rule, and the equation is only giving us the magnitude or the amount of the force or the field, and the right-hand rule is what's giving you the direction. Sorry. So this is just a short summary of how you go about making these determinations using right-hand rule number 1, number 2, and they also call this right-hand rule number 3, which I didn't point it out that way because it's basically similar to the one above it. So the first one is on the magnetic field produced by a current. The second one is the force on a current due to a field, and the last one is the force on an electric charge due to magnetic field. Now let's look at a magnetic field due to a long straight wire. Again, this is a derivation of an equation, but what we do know is that the field is always inversely proportional to the distance from the wire. So if you had a wire, basically what this is saying, and let me just change my color here. If you had a wire and you were looking at the amount or the magnitude of the magnetic field a certain distance from the wire, let's say R, and let's say this is 2R, then that magnetic field is inversely proportional to the distance of the wire. So it varies as 1 over R. So if I double the distance away, I'm going to decrease the magnetic field by that amount, or by 1/2. This can be determined, the magnetic field can be determined also based on this equation. So you can make that determination based off just the current that's in the wire. If you knew the current that's in the wire and how far away you are from that, you could determine what the magnetic field is at any point away from a wire. So here's an example. So here you've got a wire carrying a 3 amp current. A charge particle is moving parallel to it. This Q0 is some sort of test charge moving parallel and to this wire, which then will cause it to move in a circular path. And then its speed is 280 meters per second. And you want to determine the magnitude and direction of the magnetic force on the particle. So this actually involves two equations. We know that the force is equal to Q times the velocity times B times the sine of theta. We saw that earlier. But we can make this substitution if we know the distance, and if we substitute in for B here, because we don't know the magnetic field, but we do know the distance, we can calculate the force that is on that particle in the direction of the magnetic field using the right-hand rule, or the direction of that force, sorry. The direction of that force is going to be directly inward, because if that velocity is upward and the field is pointing to the right using the right-hand rule, then that force is going to be perpendicular to it. All right, so now let's say you have two wires and you want to know the magnetic field produced at a position of on wire 2 due to the current in wire 1. Again, this is a derivation. This is equation 20-2 from the text. We know that the amount of force varies as the length of the wire, and that's going to be equal to the current of 2 versus the field due to the current in wire 1. All right, so we have wire 1 and wire 2. So the force that is being exerted, F2 here on wire 2, is just going to be equal to B1, because that's that force coming from magnetic field coming from wire 1, times I2 times L2. So again, this derivation is rather lengthy, but if you've got two wires and you want to find the force of wire 2 on wire 1, this is the equation that you can use if you know the currents in these two wires, I1 and I2, and the distance that these two wires are separated by. So parallel currents tend to attract each other, and anti-parallel currents repel each other. A few other topics here. Many times what we see with magnetic fields and currents is the use of a solenoid. And a solenoid is just a long coil of wire. And we use these actually as locking mechanisms sometimes. And it's tightly wrapped, and the magnetic field in the interior here is almost uniform. And if you want to calculate out the magnetic field in a solenoid, it's just going to be equal to pretty much like we just saw in the previous equation 27, except now you've got to take into consideration N, which is the number of loops of the solenoid. So these are important because when you take a solenoid and you apply a current here, or you make a solenoid and you apply a current and you have this uniform magnetic field, it can be used for magnetic resonance imaging in the medical field, and it's a very important concept to allow you to measure or look at specific body parts. So that's one other application of it. Also used, as I said, in locking mechanisms. So if you take a piece of wire and you put it into a magnetic field, and here's an example of a switching mechanism, say a bell that you want rung, then the magnetic field increases greatly. So many times what you'll see is you'll see a solenoid, you have the, you'll see an iron rod, and you'll see your spring or your solenoid. Once you close this switch here and apply a current, what happens here is this causes the spring to activate and become pushed and causes this bell to ring. So there are a lot of applications for these electromagnets. Another application is a galvanometer, and a galvanometer can be used to measure current. And in this case, what happens is you've got a torque due to this looped current, and as you apply a current here, it causes this gauge to move, and it's calibrated to do that proportional to the amount of current that's being applied. An electric motor also takes advantage of this torque that's done by a loop of a current. And we didn't really talk about loops, the math gets a little bit more complicated. And in this way, what happens is if you've got a voltage source that's applied, this starts to move, and there's torque created, and let's say you're trying to move the wheels of the car, this causes the electrical energy can then be converted to that mechanical energy that allows for motion. So what happens is this torquing motion causes this to spin. Loudspeakers also use a principle that a magnet exerts a force on a current carrying wire, and we saw an example of that earlier. And then this is used to take electrical signals and convert them into mechanical vibrations that cause this sound to come out of these speakers. All right, one last item in this chapter, and I know I've skipped some sections, so just skip those sections, and any problem solving in those sections. One of the useful tools that we use in forensic science and other science disciplines is a mass spectrometer. And this measures the mass of an atom. And so you can measure the masses and relative proportions of atoms within a particular substance and then make a determination of the substance. And so how this works is if you have a charged particle and you move it perpendicular through an electromagnetic field, there's going to be a particular speed at which it's not going to be deflected. So if you're moving too slow, it might get deflected up or get deflected downward. But if you're moving at a certain speed, that velocity is going to allow this particle to be carried through a mass spectrometer without being deflected, and then it's going to be detected here by whatever your detector is. And that speed is proportional to the electric field, remember E that we saw previously, and the magnetic field. So what happens is that all atoms that reach the second magnetic field in a mass spectrometer are going to have the same speed, and there are two magnetic fields here. So you've got your sample, it moves here, it moves through, and anything that has the same mass is going to have the same radius of curvature, so that when it hits this detector, it's going to hit it at the same time or the same place. So this radius of curvature, as this particle comes through, is going to be equal or dependent, on the mass of the particle. So how's that used? So we know that the mass of the particle is proportional to this radius of curvature. All right. And so let's say you take carbon-12, and it's got a mass of 12 atomic mass units, and the radius of curvature is 22.4 centimeters. So you can run a known compound through there. And let's say that you then run through a compound that has an unknown element, like you're trying to figure out what something is, and you find that the radius of curvature is 29.9 centimeters. Well, we know that the masses should be proportional to the radius of curvature. That's up here, right? And so if we take those and find the ratio, which in this case is 1.33, and then multiply it by the mass of the known carbon atom, then we can make a determination of the mass of the unknown element, which in this case calculates out to 16 atomic mass units. And if we went to the periodic table, we could determine that that particular element was oxygen. So this is a way to determine unknown elements and the quantity of those. So it can be useful if you have an unknown substance, if you know all the elements, and then you can quantitatively determine their ratio, you can figure out what the substance is. All right, so summary. Magnets have north and south poles. We know like poles repel, unlike attract. Units of magnetic fields are the Tesla. And I'd recommend for the final that you have a list of units and what the variables are. For example, B, Tesla, Q, coulombs. This might help you when you're reading through a problem to understand what topic this might be from. We know that electric currents produce magnetic fields, and the field exerts a force on an electric current, and that's equal to this equation. And if there's a moving charge, the field exerts a force on a moving charge. And we also talked about the fact that if you've got a long straight current carrying wire, there's going to be a magnetic field on it. We know that parallel currents attract, anti-parallel currents repel. And finally, we talked about quantitatively that the magnetic field inside a solenoid is equal to mu0, which is the permittivity in free space, times the number of turns times the current over the length. And then the final topic we talked about was mass spec. And I gave you a short example of how to do a problem to solve for the mass of an unknown element.